They are called the superheroes, silent superheroes of computer programming, because they are just this piece of code that works on the background to help you pack your poop and dispose them whilst you're initializing and assigning variables throughout the life cycle of your program. They are called garbage collectors. I'd never really understood how these guys work, aside from the fact that I know that there is something in the background of whichever programming language I'm using that helps me with memory management and helps me not to blow up my RAM. But I started to get curious, a little bit curious, and I decided to run down the rabbit hole of understanding the various algorithms that these garbage collectors uses. And I also set out to understand how garbage collection actually works in 4 different languages. It is in Java, .NET, Golang, and Python. And so in today's video tutorial, I'm going to be sharing with you how garbage collection actually works, the various algorithm garbage collector uses, and how garbage collection works in all of these programming languages that I've listed. How about we dive right in, guys? So just to throw a little bit of caution out there, the video you're about to watch actually contains a number of information and it can be overwhelming, can be pretty overwhelming. It's just the fact that I am not a language optimist, I'm an engineer. So if there is any information in a particular language I do not write, I do not mind going to learn whatever information it is I have to learn, get to use it and probably leave the language alone. If you are not that type of person, you can easily just keep over to how garbage collection works in the particular language that you write. But if you're as curious as myself, you can just watch the whole thing and take it bit by pieces. So let's get into the real stuff. All right, let's get into it, guys. So to understand garbage collection, you first need to understand the concept of these 2 types of memory, which is stack memory and the heap memory. And this is not necessarily stack and heap in your data structures and algorithm. All right, they are not necessarily related. The stack memory is basically a type of static memory that is used to store local variables. Most of the time, variables that are usually within the scope of a particular function, they are short-lived. This stack memory is managed by the operating system. So the operating system does the memory management of this stack memory. And the second type of memory that we have on the other hand is the heap memory. The heap memory is a type of dynamic memory. Whilst for the stack memory, you need to know the amount of size of whatever it is that you want to save in it. Hence the reason why it is static, it can be resized. But for the heap memory, you're allowed to save dynamic data structures, dynamic variables, usually used to save global variables. All right, so you do not need to know what the size is. You can just save the thing in there and the thing can keep growing in the heap memory. All right, now this heap memory is not managed by the operating system. Somehow we have to figure out how to manage this memory, and this is where garbage collection comes in. I know you guys are new age programmers just like myself, but in programming language like C and C++, you as the programmer do not only worry about your business logic or how the structure of your code looks like. You also have to worry about how to allocate and deallocate resources, objects in your memory. In this particular heap memory that we're talking about, you have to worry about how that is going to be done. So heap memory is where memory management is required. So having understood that garbage collectors are actually needed to manage the heap memory, we're going to be talking about the top algorithm that is used in garbage collectors, all right? And that is going to be opening up the way to talk about the programming languages that actually uses those algorithms, all right? So the first algorithm we're going to be talking about is the mark and sweep algorithm. Yeah, literally like mark, sweep. So in mark and sweep algorithm, the garbage collector actually splits its functionality, its duty into 2 parts, which is the marking and the sweeping. So in the marking process, what the garbage collector basically does is to go to the root node of your program, which is basically your process. Your program is running a process. So it goes to the root node of the process and then it begins to mark all of the resource, which are your objects, all of the objects in the memory that is reachable to the process, that is attached to the process. So it begins to mark every one of them. And during that marking phase, the garbage collector would be able to spot all of the objects that are no longer reachable to the process. Maybe for one reason or the other, they were initially spawned by the process, initialized, assigned by the process. The process was using those objects, but for one reason or the other, they are no longer reachable to the process. So the garbage collector is able to identify all of those objects, and they are not marked. The only objects that are marked are the objects that are reachable to the root process. Then at the sweeping phase, which is the second phase, the garbage collector simply sweeps, which basically can be called dispose, simply disposes all of the unreachable objects to your process. And that's how the mark and sweep algorithm works. One of the languages that uses this mark and sweep algorithm is Java programming language. And we're going to be talking about how garbage collection works in Java programming language. So the Java team actually uses mark and sweep in its simplest format, in its finest format. All right. But as time began to pass by, the Java team began to realize that mark and sweep in its unadulterated format is actually not scalable, because as your program begins to grow, the size of your objects within your program began to grow as well. For large scale programs, the size of the objects in the memory would grow as well. And as the objects increase, the garbage collector began to take an enormous amount of time to be able to dig deep into marking objects that are reachable and also sweeping objects that began to cause for performance issues. So the Java team set out on a particular research, and this research showed that objects are actually short-lived. That then introduced a concept called generational garbage collection in Java. The concept of generational garbage collection is, rather than having to throw the garbage collector into the deep end of the heap memory to search down objects, the heap memory is divided into three generations. First is the young generation, second is the old generation, and the third is the permanent generation. So garbage collection would now work in these three different generations, rather than having to work in all of the heap memory at the same time. So having discovered this concept of generational garbage collection, Java then introduced four different variants of garbage collectors, and also gave developers the ability to be able to switch within any of these garbage collector depending on the use case of the solution they're trying to build. The first variant is the serial garbage collector. It is a stop the world type of garbage collector, and what stop the world basically means is when the garbage collector wants to work, it halts the program process so it can work. Although the time is very minimal and you would not even notice, but as the scale of the program begins to get large, you might begin to notice. And that's why this particular type of garbage collector is used for relatively small projects. The second variant of garbage collector is called the parallel garbage collector. It is the default garbage collector for JDK8. It works on multiple threads and it's able to perform compaction. So the concept of compaction is this: when memory is being freed in the heap memory, there is the problem of fragmentation. So what that basically means is, in the heap memory, because memory is not freed contiguously, this portion of memory can be freed, and the next portion of memory that will be freed is in this particular place. The next portion of memory that will be freed is in another long distance. All right. Now, if there is a process that needs to use an amount of memory space, that amount of memory space can be available if you sum up all of the free memory. All right. But because they are not contiguous, because they are fragmented, the resource would not be able to use the memory. So the only solution to that is what is called compaction, which is to bring together all of the free memory so it can be useful for use. And that is what parallel garbage collector actually does. It does compaction. It is also a stop the world type of garbage collector. I'm sure you understand what stop the world means now. Another variant is called CMS, concurrent mark and sweep. This is basically a variant of mark and sweep. However, this one works on a multiple thread. So in some particular phases, it still maintains the stop the word concept, while some phases are concurrent. However, the pauses are very minimal compared to the original mark and sweep or compared to, say, serial garbage collector. The next variant of garbage collection is called G1GC, as garbage first garbage collector. This is the default garbage collector for JDK9. It basically works on a large scale project, large heap size memory. And this works by dividing the heap size into chunk of 1 MB to about 32 MB. My memory serves me right. Yeah, it works. This actually performs pretty well. It is concurrent and it works really fast, designed for large scale projects. Another programming language that uses the mark and sweep algorithm is .NET C#. .NET also uses mark and sweep. However, .NET also does the generational thing, generational garbage collection. So it has generation 1, generation 2, and generation 3. Garbage collection occurs individually in these different generations. And there's also the concept of promotion of objects. So objects can move from one generation to another. All right. So at the very core, it does mark and sweep. However, it does it in a very efficient manner. Another language that uses the mark and sweep algorithm is Golang. In Golang, mark and sweep is divided into three phases. The garbage collector divides mark and sweep into three phases. The first is the mark setup. The second is the marking, the actual marking. And the third is the sweeping. So when Golang garbage collector actually starts, during the mark setup phase, the first thing the garbage collector actually does is to initiate the write barrier. And the reason it does that is to make sure that the collector maintains data integrity, because the garbage collector and the application have their different coroutines. And if they are allowed to work concurrently, there is going to be race condition. So during the mark setup phase, Golang garbage collector initiates what is called write barrier. So the application is unable to mutate the data whilst garbage collection is going on. So obviously the next phase is the actual marking, where the garbage collector, the same process from the root node, marks all of the different objects that is reachable from the process. And that's a concurrent process actually, that because that's one of the reasons why garbage collection is actually very fast in Golang, because the marking phase is a concurrent process. It doesn't stop. It doesn't make the application stop before it has to do marking. And the final part is obviously the sweeping. That is a stop the word process. However, this process is usually very negligible, usually between 10 to 30 microseconds. So you're actually never going to notice. So another algorithm used in garbage collecting is reference counting. And the language that uses reference counting is Python. So the concept of reference counting is such that the garbage collector keeps a reference count of every resource that is assigned to a particular program. So as you add that particular resource to the program, the reference count increases, and as you remove the resource from the program, the reference count decreases. Immediately the reference count hits 0, the garbage collector basically sweeps out that particular resource from the memory, just frees the memory of that particular resource. But one of the problem with reference counting is the fact that it is unable to undo cyclic references, and that's a problem. So what Python basically did was to use reference counting as their primary collector, and to mitigate the issue of cyclic references with a cyclic garbage collector, right? So it uses reference counting and a cyclic garbage collector to undo cyclic references. So that's basically how Python garbage collector works. All right, guys, that will be it for this week. If you're yet to subscribe to this channel, make sure you hit the subscribe button. Put a comment in the comment section below if you found this helpful, and also do well to share this with your colleagues at work, your colleagues, friends, and family. See you guys on the next one. Have a great one, guys.